The 360 on Energy and Carbon, hosted by 360 Energy. On today's episode, we are joined by Kirsten Hannum and Elizabeth Houghton. Kirsten completed a MSc in Forest Science at the University of British Columbia and a PhD in Soil Science at the University of Alberta. She has worked for the British Columbia Ministry of Forests, for Natural Resources Canada, and for the University of British Columbia, Okanagan. Her research program has two main objectives. One, to explore the potential of agriculture to help mitigate climate change, and two, to identify tools to help farmers adapt to climate change and weather extremes. She has published several peer-reviewed papers on soil carbon, nutrient and water management in agriculture and forestry. She is one of the science team co-leads for AAFC's Agriculture Climate Solutions program in British Columbia, is co-chair of the Agriculture and Water Committee for the Okanagan Water Stewardship Council, and serves on the steering committee of BC's Agriculture Climate Adaptation Research Network. All presentation by AAFC research scientist Kirsten Hannum is copyrighted under His Majesty the King 2020, licensed under CC-BY-NC 4.0. Elizabeth Houghton was born and raised in southern Ontario but moved west to the Okanagan Valley of BC to complete her BSc in Earth and Environmental Science at the University of British Columbia, Okanagan. She is currently pursuing her PhD in biology at UBCO. Working with local commercial cherry growers and in collaboration with Agriculture and Agri-Food Canada, she is researching the impacts of post-harvest deficient irrigation on sweet cherry with the aim of enhancing the BC cherry industry's resilience to climate change and improving sustainable irrigation management practices in the Okanagan Valley. Elizabeth's research was supported by the Canadian Agriculture Partnership, a federal provincial territorial initiative, and delivered by the Investment Agriculture Foundation of BC. Now let's get into the episode with Kirsten and Elizabeth.
Well, welcome back, John. Nice to see you again.
Yes, it's nice to be back, but it seems a little bit strange not having Lysandra to keep us in order, doesn't it?
Well, this will be a challenge, and she might get a chuckle from our questions as we go forward. So we're very fortunate to have some guests with us today. And to be clear to our listeners, today we're going to be talking about climate modeling and application. And we're fortunate to have Kirsten Hammond with us. And Kirsten, would you be kind enough to sort of explain your role and what you do?
Sure, I'd be happy to, David. My role at Agriculture and Agri-Food Canada is officially called a systems agroecologist. I'm based at the Summerland Research and Development Centre in British Columbia, and I largely focus on the use of agriculture in woody perennial crops like grapes and cherries and apples to help mitigate climate change, so reduce the effects of climate change by limiting the amount of greenhouse gases we produce and increasing the amount of soil carbon we generate. And also a second role is to help us adapt to climate change. So anticipate how climate change is going to affect agriculture in this region in the future and how we might change our practices to help us continue to grow food despite these climatic changes.
This is going to be a really interesting topic for our listeners, but I can tell you, I live in the Niagara Peninsula. And so it's right up the alley, and I grew up on a farm. So I'm really looking forward to hear this as well. And I think you also have another guest that's with us as well. Did you want to introduce Elizabeth?
I'd be happy to. Elizabeth is an extra special guest here today. She's a PhD student who's working with me and my colleague Denise Nielsen, who's my predecessor here at Agriculture Canada. And Elizabeth has really been digging into how to develop a model for cold hardiness in cherries. And I thought she would be able to answer questions about how models are developed and how they might be useful in anticipating effects of climate change for specific agricultural crops.
Wonderful. Well, thank you, and welcome to you both. This is going to be a really fascinating session. And, a lot of times people take agriculture for granted, and they don't realize the importance of it and what it can do, not only for our economy, but also certainly sort of for society itself. So I'm really looking forward to this session. So I'm going to start out with the first question. And that is, what do you deem as climate modeling?
This is a great question. We talk about climate modeling all the time, and I was contemplating last night, how exactly do I describe it? And I think essentially climate modeling is weather forecasting writ large. So when we think of weather forecasts, they're usually tailored to a specific area and a short period of time. And they consider the current weather, air temperatures, wind direction and speed, local topography and water bodies. And they're really looking forward to the future only about a week or two. Whereas climate modeling is using a lot of those same principles, but just over a much wider area and for a much longer time period. And there are kind of two main climate type model types that we talk about. Sometimes you'll see the acronym a GCM. It stands for a global circulation model. And these models basically integrate a whole bunch of equations, mathematical equations that describe physical processes and how we understand them to work. So they include mathematical equations that describe what happens to the sun's energy when it hits the Earth's surface, how much bounces off, how much is absorbed into the atmosphere, and what happens to that energy once it's in the atmosphere. It includes other equations that describe how air and water flow over the Earth's surface and how temperatures affect the amount of water that can be held in the atmosphere and at what point it comes back to the Earth's surface. So all of these different kinds of physical equations that explain how physical phenomenon in our environment have been all put together into a big model to try and understand global phenomena that are relevant to what eventually produces a climate. But there's a second type of climate modeling called an Earth systems model. And I've heard it described as a pimped up version of a global circulation model. And these type of models include equations that help us understand chemical processes and biological processes in addition to those physical processes that the global circulation models describe. So these incorporate phenomena like what happens when there are extra particles in the Earth's atmosphere and how does that affect how much water falls and when it falls to the Earth. It helps us understand how temperature and moisture affects which plants grow and where across the Earth's surface, and how carbon is pulled out of the atmosphere through photosynthesis, incorporated into plants, and then how it's moved back, that carbon is moved back up into the atmosphere as plants decay. So these are essentially a compilation of a whole bunch of different equations that explain small parts of our understanding of how the Earth works. And when they're put together, it tries to create a picture of how our climate will change given different conditions.
And so this is not something faint of heart. This is quite a bit of knowledge and detail and variables that you have to consider when you're doing this modeling.
And a huge amount of computing power.
Yes, yes.
Yeah, I was listening to that. I guess one of the things that's enabled climate modelling is, of course, the development of computer power. Because if we went back 50 years, how would you model the climate? I think you did everything based on what it used to be and sort of historical readings, didn't you?
That's very true. And we also had to use much more general data sets. So the resolution of the data we were looking at was much higher.
Yeah.
Now our climate models are capable of looking at 50 kilometers square grid cells across the Earth's surface, whereas before those grid cells were much larger.
Yeah.
So as our computing power has gone up, we can look at more high resolution data, we can project farther into the future, and we can incorporate more and more processes.
I think it's a fascinating area. It's one of these things. I mean, we focus on carbon emissions, energy, and things like that, but there are so many topics that are going on around it, and it's quite interesting. I was just reading something the other day, and somebody was talking about having carbon tunnel vision, where you're just focusing on carbon emissions and not thinking about the other aspects around it. And based on that, my question is, so why is climate modelling important to the agriculture industry?
This is another great question. I was trying to imagine another industry that is more dependent on climate and weather than agriculture. And I can't really come up with one, honestly. For agriculture to be successful, we need to make sure that the growing season is long enough in the year, that temperatures are warm enough that crops can mature, that they have enough moisture to grow. We have to make sure that there aren't sudden drops in temperature through the growing season that kill the crops. And in the winter, for perennial crops like those I work with and those that David is familiar with, we need to make sure that temperatures get sufficiently cold in the winter, that dormancy can be broken. So it really affects how well plants grow and where. But it also affects other things we don't think about quite as much. Moisture and temperature conditions determine how organic matter decays in the soil. And that organic matter decay is really important because it releases nutrients for plants to take up. So if it's too hot or too cold or too dry, that process doesn't occur as well. And it also really affects how pests and diseases and pollinators contribute to or are detrimental to crop growth. So pests, as temperatures get warm, insects have shorter generation times, and so they can become an increasing problem. Fungal diseases can really be promoted in more humid conditions. And our pollinator friends, the bees, need nice, perfect, warm conditions so that they can do their important work of pollinating flowers. So all of these processes are dependent on weather and climate. And I just can't think of another industry that is more linked to temperature and moisture conditions than agriculture.
Yeah, it's interesting. Whilst you asked, I was thinking, oh, what other industries? Oh, tourism, but that's a bit of a weak link, isn't it? You really haven't got anything like that. And I guess as well with modelling is a part of what we're doing, looking for prediction, so that presumably the industry can then decide, does it have to move where it grows particular crops? Does it have to change what crops are? Is that one of the outcomes of the modelling?
Yeah, climate modeling can help agriculture in a number of different ways. First of all, we can use historical moisture and temperature data to understand those processes that drive biological, chemical, physical processes. So we can look at insect development through the growing season, for example, and relate it to the temperature conditions that we observed. And over multiple years of observation, you can start to understand how these things are related. And after you've used past weather data to develop an understanding of how a system works, then you can use these climate projections into the future, built with global circulation models and Earth systems models, and plug that future anticipated weather conditions into the model to understand how these biological processes might occur in the future.
It's pretty important, isn't it? Because we this week, isn't it? We've just gone over 8 billion people in the world, and we've got to feed them,
Yeah, it's food security is a huge issue and is
isn't it?
very, very dependent on climate and
Yeah.
climate change. Hmm.
Thank you. Dave, over to you.
So, Kirsten, I totally agree that weather is a massive factor to this industry, and it always has. But because of climate change, now you have long-term ramifications on what type of crops you're going to grow, where you're going to grow up. So I really see how this is so important for us to plan what we're going for. But my question to you, and I think maybe yourself and Elizabeth maybe I want to respond to this, but can you provide any examples of how climate modeling can be a benefit to the agriculture industry, like in BC, for example, the orchards and stuff like that?
Yes, I definitely can. A lot of it was driven by my predecessor, Denise Nielsen, who has been working in crop suitability modeling in agriculture for several years. Agricultural producers are noticing changes on the ground and adapting to them even before we develop the models to explain what they're observing. And this is a great example. So we've noticed that sweet cherry producers are planting orchards farther north than they have ever been able to and higher up in elevation. And this suggests that they are observing that temperatures are warmer in these areas than they have been in the past. And as a result, they can actually produce crops in cheaper areas that weren't considered appropriate for fruit tree production in the past. Denise and her colleagues developed a model that looked at the climate suitability of sweet cherry all through the growing season. So this model incorporated information on what temperatures are required for the crop to have sufficient warmth to produce a crop through the year. It incorporates information on what temperatures are too high that they might damage the fruit. And it also incorporates information on under which conditions do the temperatures become too cold and when through the year that fruit buds might actually be damaged and crop yield losses will result. So that part of the overall crop suitability model, the cold hardiness model, is a piece that PhD student Elizabeth Houghton has been working on refining. And so I thought I would turn that work over to Elizabeth to describe, and maybe she can talk about how that model is developed and what data are used to run that part of the model.
For sure. Thanks, Kirsten. So the models that Denise initially developed on crop suitability were missing a key part. They still did a great job making predictions, but they didn't have data or models that were able to predict cold hardiness. They were using models that predicted other aspects of plant dormancy instead. But what I've been developing based on this work that Denise has done are models that are able to predict the temperatures that cherry fruit buds can withstand throughout the winter time. This is important for growers because the cherry fruit buds are associated with high economic value. They're what produces the cherries in the following season, which ultimately is the goal for these cherry growers. So I've been working with equations that Denise developed for dormancy to develop models that are able to determine these temperatures that the plants can withstand. And moving forward, this could contribute to the crop suitability modeling to estimate where these plants could be established in the future in British Columbia by refining these aspects of modeling related to cold hardiness. It must be noted that sweet cherry crops can be extremely susceptible to severe winter temperatures or rapid changes in cold, whether this occurs in the fall, the winter, or the spring. And modeling crop suitability based on climate change in the future may help us predict where these crops may be able to be established in future climate change scenarios. However, they may have difficulties accounting for things that we might not be able to predict quite as well, like rapid changes in temperature or more extreme weather events.
So for our listeners, because we have a variety of listeners that are from industry, from agriculture, from around the world, if you're not in the agriculture sector, I think most people aren't aware, like when you plant a tree, production may not happen for 3 to 4 years until you get full production. That's quite a commitment that a grower has to make in deciding where to plant a tree. And then, in industry, they're used to a 1-year payback. And so this is why it's so important for the modeling that you're doing is to help growers feel confident and confirm where they want to go. Because essentially, if it takes 3 to 4 years of production and you pick the wrong location, that's a lot of money wasted and food production that's not there. So I can see really the importance of what you just discussed.
And David, maybe Elizabeth, given what you've said, would like to talk quickly about the model's use as a decision support tool for cherry producers within given years. Do you want to talk a little bit about that?
Sure. Yeah, so these models have been developed so that growers can access them in real time, so that they're able to plug the weather data that they've seen throughout the season, mostly starting in the fall and the winter seasons, to determine the temperature that day that their crops can withstand. And this can act as a decision support tool because it can help growers decide if they need to take frost protection management measures moving forward if they think that the temperatures that they're about to experience in their orchards are going to fall below the temperatures that their plants can withstand. This is important because applying frost protection measures, such as using fans to help move the cold air off the crops, can be quite costly. So having a model or a tool that can help growers make these decisions will be beneficial for them moving forward.
I'm going to pick up on that because that is great information. And so the question for yourselves is, are you getting a sense of, and I could appreciate maybe this modeling's new, but are you getting a sense of the sort of a cost benefit or productivity improvements or longevity of the trees because growers have this information and they can take action? Are you getting any sense of the payback associated with having this modeling?
We haven't done a specific cost benefit analysis on these models. However, the modeling that I've been doing has been looking at just the frost susceptibility of the sweet cherry bud. So you could get 100% damage of sweet cherry buds and your trees will still produce buds in the following year. I'm not looking at damage of the tree overall.
Okay, fair enough. But it does have an impact on the actual production. So they do have.
Absolutely.
Yeah, okay, thank you.
So it's kind of an example that the way Elizabeth just described the use of this model of differences in weather data versus climate data. So this cold hardiness model that Elizabeth is describing, once it's available to farmers and they learn how to use it, they could use weather data from the previous few days to anticipate for that year what they might be able to do to protect the buds that are developing on that tree for the next growing season's crop. But then if we look at the overall crop suitability modeling that Denise has been doing, which will incorporate that small part of Elizabeth's model into it, that's looking at overall climate effects on where you might want to establish orchards in general in the future and how likely it is that you will be able to grow successive years of crops. So they're almost on two slightly different scales and allow you to plan in one case a few days ahead and in another case over a few decades.
It is amazing the power of technology if you know how to use it and how you use it. That's a great example.
This has been absolutely fascinating because we tend to, I think this is an educational thing, isn't it? You know, we had a thing here in the UK where they asked children where carrots came from and they said the supermarket, completely forgetting the fact that they had to be grown. So I think we're talking about an important subject and education is an issue. But my question to you is, what are some of the particular challenges with climate modelling and its application?
A couple that come to mind are just limitations really in our modeling power. Elizabeth raised this in her earlier answer that it's very difficult for us to predict extreme events. So, for example, an atmospheric river hit us on the West Coast last year, and researchers have done some modeling to determine that that atmospheric river, which caused a massive heat event early in the growing season last year, was probably related to climate change, but the occurrence of those events is very difficult to predict. So climate projections using these global circulation models, for example, tend to show patterns in climate, but they can't predict these extreme events so easily. Sudden heat, sudden rain events, sudden drought. Another issue with them is that precipitation is very difficult to predict accurately. And so climate modelers, I think, in general, feel more comfortable with projections of temperature patterns through time, but precipitation is harder. And one of those reasons is because precipitation is so strongly affected by topography. And that's really hard to incorporate into your model and make it meaningful across the landscape. And We were also talking about how increasingly climate models are becoming higher and higher resolution. So our ability to predict precipitation into the future is getting better because we can incorporate that smaller scale topography. But in general, the predictions are still done at about a 50-kilometer scale grid size. And in regions like the Okanagan Valley, where there's a lot of topography over a very small scale, it's very difficult to get accurate climate projections at a scale that's meaningful to us. So there are still a lot of challenges. And I guess one final challenge might be that, particularly in areas like the Okanagan Valley, where it's so topographically complex, we need really good high resolution weather data. That weather data can be used to build those future climate models or future climate projections. And we are always constantly complaining that we don't have enough good quality weather data and good quality weather stations installed across the landscape. So that's definitely another big challenge for us.
You share the same problem as everybody, poor weather forecasts.
Yeah, it's interesting. I hear it all the time from in so many different fields. So it's interesting that you do too.
Yeah.
All right, so we're at the end of our podcast here. I have one last question for yourselves. Can you share with me, based on what we've discussed today, what do you think is the biggest takeaway for our listeners?
I think the biggest takeaway from my perspective is that climate modeling is our best guess of how the world works. It is kind of the result of a whole collaborative effort. We're standing on the shoulders of giants here where mathematicians and climatologists and biologists have all collected little bits and pieces of information that have been used to build a big model or picture of how our world works. And these models are now big collective tool that provides us with a lot of information about how our world works and what we might anticipate from the future effects of climate change. And these tools are also really powerful because they can help us figure out how to adapt to climate change. If we know what might be coming, we can start to think about how we'll adapt in the future, which is particularly important for agriculture because we might need to start growing different crops in different places or growing them in different ways. And finally, I think climate models really also help us marshal our efforts to mitigate climate change in the most effective way possible. So we can use climate models to tweak different parts of our system to say, okay, what happens if we try and reduce atmospheric CO2 concentrations in this way? What happens if we try and reduce nitrous oxide emissions in that way? And by using these models, we can get a best guess of what mitigation efforts might be most effective. So they're a really, really useful tool. They don't tell us the exact answer, but they can give us a best guess.
Thank you. And John, how about yourself? What would be something that you captured from this
Yeah,
discussion?
I think what this podcast has reinforced to me is that we tend to forget that we are players in an incredibly complex system and that, the cause and effects we don't really know. And the more that people like Kirsten are doing modelling, the better chance we have of, shall we say, making less mistakes in the future.
I think what I captured is modeling is really important. I didn't truly, we work in the greenhouse sector quite a bit. And so we do modeling because we have real data, like detailed data. I didn't realize the power and the importance of outside crops and how they could be used, truthfully, I guess, because we're just not limited, and how modeling is important to every industry, agriculture, whatever. And I think it's a difficult challenge because of all the variables we've talked about, but I think that we're all going to get better at doing this as we get more and more experience. I don't expect perfection for sure, but I think it will be a requirement or a need going forward just to make sure we're optimizing and doing the right thing, or else we will be in trouble. So I want to thank Kirsten and Elizabeth. Thank you so much for your time today and appreciate what was stated. John?
Thank you, everyone. That was a really interesting session.
Thanks for the opportunity.